Hello everyone. Today let's solve the problem number 23, merge k sorted list. So you can just go through the question and you can just try to understand the question with the examples that they have given. I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given an array of k sorted lists. So we have given an array of k sorted lists, sorted linked lists. Each linked list is sorted in ascending order. So here you can clearly see each linked list is sorted in ascending order. You can clearly see this one. The task is to merge all these sorted linked lists into the single sorted linked list and return it. So our main task is to merge all these sorted linked list into the single sorted list and return it. You can clearly see here. So the linked list they have given here is 1, 4, 5. The first one, the second one is 1, 3, 4. Second one, third one. Merging this one, so we are getting here in the base of ascending order, right? 1, 1. This one we are merging. Next comes the 2. Next comes 3, 4, 5. 4, 4. Twice 4 is present here. Finally 5 and 6, right? So that's what they have shown in the output as well. Same goes with the example 2 and example 3. Suppose if we don't have any elements within the array, empty array consists of empty array output, and suppose we don't have any elements in the array at all, then we are displaying the empty array as the output. That's what they have given here. So let's discuss the approach first. I hope the question is completely clear. Next, let's discuss the approach. After discussing the approach, let's go with the edge cases. After discussing all the edge cases, finally, let's write the code and discuss the complexities of the code that we have written. Initially, let's go with the approach. So let's discuss the approach step by step. Let me give here approach, right? So we'll be making use of the min heap or the priority queue. Just keep in mind, we'll be making use of the min heap or the priority queue here. And we'll be going with the min heap or the priority queue approach. So what's the first step here? So we are adding the head node of the each linked list to the priority queue here. We are adding the head node of each linked list to the priority queue. Why we are making this one? Why we are adding the head node of the each linked list to the priority queue? Because then only we will have the smallest value from the each list that is available. So to get smallest value from each list, right? This is the reason we are adding the head node of the each linked list to the priority queue from the each list. So we are adding the head node of the each linked list to the priority queue just to get the smallest value from the each list, right? This will be the first step. I hope this is clear. Let's move on to the next step. Nothing but we have to remove the smallest value from the priority queue now and add it to the merged linked list. Here what we are doing, remove the smallest value from priority queue. We are removing the smallest value from the priority queue and we are adding it to the merged linked list, right here. What we are doing in the second step, we are just removing the smallest value from the priority queue and finally we are adding the same to the merged linked list. Let's move on with the third step. Nothing but if the removed node has next node. So we are removing here smallest value from the PQ, right? If the removed node has this one next node, then what we will do, we will add that node to the priority queue. If the removed node has the next node, then we are adding it to the priority, that node to the priority queue. This is fine. Basically, this we will continue until all the nodes are processed. Finally, we are just returning the merge list. So we'll get the merged linked list in the sorted order, right? Finally, what we'll do? We have to return merged linked list here. This is fine. So this is the approach that we will be following. But first step is we are adding the head node of the each linked list to the priority queue. Why? Because we have to get the smallest value from the each list. So the second step is we are removing the smallest value from the priority queue and we are just adding it to the merged linked list. This one, second step. Just give me a second here. Second step. And finally, third step is if the removed node has next node, then we are adding that node to the priority queue. Finally, after that one, we will just continue until all the nodes are processed, then finally return the merged linked list. So this is the approach that we are going with. So let's discuss edge cases step by step or one by one. So I'll just come here. Let me give here edge cases. So here, the first edge case here is when the input, just give me a second here. When the list says empty. So let's go with the empty input. So suppose input, let me consider here lists. This one output will be empty as well. We saw this one in the example as well, right? So here no linked lists are given. So the output will be an empty list. So this is for the condition empty list. This is fine. Empty list, or we can just consider here empty input. This is first one. So let's move on with the second edge case, nothing but input with one empty linked list. So while I say one empty linked list, we can just consider this one. The same thing that they have given in the example. This one output will be empty. Why? The input contains an empty linked list. That we know that, right? Here you can clearly see the input consists of an empty linked list resulting in an empty output. This one. So this is for the input with one empty linked list. This is fine. This is for the second edge case. Let's move on with the third edge case. Nothing but two linked lists with no overlap. So while I say two linked lists with no overlap, let me consider here lists. This shouldn't overlap, right? So let me clearly give 1, 2 and 3 here. This is fine. So the output will be here 1, 2, 3. So here we have the two sorted linked lists that are not overlapping, right? That are not overlapping. So they are simply concatenated in the sorted order. So this is for the condition two linked lists with no overlap, right? So let's move on with the final edge case or the fourth edge case, nothing but general case with multiple lists. So when I say general case with multiple lists, I'll just consider this example 1, 4, 5, anything you can consider here. Let me consider 1, 3, 4 and 2, 6 here. This is fine. So the output will be here same as example 1. 1, 1, 2, 3, 4, 4, 5 and 6 here. So this is for the condition general case with multiple lists. This is fine. So here multiple sorted linked lists are merged into one sorted list basically, right? So these are the edge cases that we have to keep in mind. First edge case is here empty input. The second edge case here input with one empty linked list. Third edge case here is two linked lists with no overlap. The fourth one is general case with multiple lists. So these are the four edge cases that we need to consider, right? So now let's start writing the code. And I'll explain the code while writing the code itself, and then finally discuss the complexities of the code that we have written. Let's start writing the code here. First, as usual, we had discussed in the approach this one. Let's initialize an minimum priority queue to store the node values in the ascending order. So I'll just give here like priority queue. Let's create the min priority queue here. I'll just give here priority queue here, priority queue. This is fine. So after initializing the min priority queue, let's add all the node values from the lists to the priority queue. For this, I'll just make use of the simple for each here. This is fine. For each. So n, let me consider here while of n. Then I'll just go with priority queue dot nq. Nq is fine. So value of the n, right? So I can just write n this way, n dot val. Nq is nothing but adding. We are making use of the queue, right? So we are going with the nq. So what we are doing here, while of n y, we are just traversing through each linked list here by making use of n. Here this one, we are just adding the nodes value to the priority queue. So after adding the nodes value to the priority queue, obviously we have to move to the next node, right? So for moving to the next node, I'll just give here, I have considered n here, right? N dot next. So this is fine. So after this, what we'll do, if the priority queue is empty, then let's return null. We don't have anything, right? So then let's return null. This is one of the edge case. So I'll just give here pq. We have seen this edge case already, right? Size. Then what we will do, we'll just return null in our case. This is fine. So after the after that case, after the previous line, I mean, what we have to give here, let's create the, what we have to do here, let's create the head of the new merged linked list using the smallest value here. So in simple terms, I'll just give you a head equals new list node of pq dot dq. This one is fine. This is also fine. Element. This is fine. Finally, let's consider the pointer to the current node in the merged list. So I'll just give here current equals head. This is fine. Finally, after this step, we have to process the rest of the priority queue and build the merged linked list, right? So for that one, what I'll do, I'll just make use of the simple while loop. I'll just give here priority queue dot size. So this is function, right? This is fine. Current dot next. So let's add the smallest value here again. So I'll just give here list. I need to consider list node here. For adding, I'll just make use of the we have to add the smallest value, right? So we have to remove the element. So from the priority queue. So for that one, I'll just be making use of the dq here. dq element. This is fine. So finally, let's move the pointer to the next node. So we have the current here. I'll just give you a current dot next. This is fine. So finally, the final step is we have to return the head of the merged linked list to get the result. So let's return head here. So I hope this is clear. Let me format the code once and let me hit the run button. So you can clearly see the sample test cases are getting passed here. Let me hit the submit now. So you can clearly see here all the test cases are getting passed here. This is fine. So now let's quickly discuss the time complexity and the space complexities of the code that we have written. So the approach that we went with here is minimum heap or min priority queue. That one we know, right? And what will be the overall time complexity here? The overall time complexity would be big O of n log k. So by here the time complexity would be big O of n log k here. N is nothing but we know that it is total number of nodes across all the k lists. N is nothing but total number of nodes. K is nothing but k lists, right? So here each insertion or deletion in the priority queue takes log k. So we have considered lists as k, right? So each insertion or the deletion in the priority queue takes big of log k. So we are doing this for every node. So overall time complexity would be n log k, quite obviously. So next step is what will be the space complexity here? Overall space complexity would be here big O of k. Why the space complexity would be big O of k here? Because we know that the priority queue stores at most k elements at a time. Priority queue stores at most k elements at a time, where k is nothing but the number of lists here. So overall time complexity would be big O of n log k, and the overall space complexity would be big O of k here. I hope this is completely clear. I hope the solution is completely clear, right? For now, this is it. Thanks for watching, guys.